Electrochemical reactions. The basis of electrochemistry is the electrochemical reaction. This type of reaction involves the transfer of electrons from one molecule or ion to another. Electrons are transferred to another atom or molecule. They do not just go away. There must be the same number of electrons after the transfer has occurred as there were before the transfer. Because the electrons are transferred, there is oxidation and reduction that has occurred, and the reaction is a redox reaction. To help keep track of the electrons, we assign each atom an oxidation number. We've already talked about oxidation numbers. This is a convention, an agreement among chemists, to assign the electrons to particular atoms as if they had actually been transferred from one atom to another, even when the species is molecular and the electrons are being shared. A species is oxidized when it loses one or more electrons. That is, oxidation is the loss of electrons, or the increase in the oxidation number. In this case, zinc's oxidation number increases from 0 to +2 as it loses 2 electrons. A species is reduced if it gains one or more electrons. That is, reduction is the gain of electrons, or the decrease in oxidation number. In this case, hydrogen is reduced because its oxidation number goes down from +1 to 0 as it gains electrons. The species that contains the atom that is reduced is called the oxidizing agent. In this case, it is the H+. The species that contains the atom that is oxidized is called the reducing agent. In this case, that is the zinc metal. Let's review the rules for assigning oxidation numbers to atoms. Rule 1. Elements in their neutral elemental form have an oxidation number of 0. These are things like O2, C, Xe, S8, aluminum metal, and anything that is an element with no charge. Rule 2. The oxidation number for a monatomic ion, either positive or negative, is the charge of the ion. For example, Cu2+, O2-, or Cl-, but not I3-, Hg2 2+, or O2 2-. Rule 3. If two nonmetals are bonded, the more electronegative element is given the electrons. If the two atoms are identical, the electrons are split evenly between the two. This means that nonmetals usually have negative oxidation numbers, though some can be positive in certain situations. Two particular ones to remember, because they often occur in compounds, are oxygen is usually -2, and hydrogen is usually +1. Since fluorine is the most electronegative element, it will always have an oxidation number of -1 in compounds. Other halogens are -1 when they are the monatomic negative ion, but will often be positive in other compounds, particularly if they are in an oxyanion. Rule 4 simply states that all the electrons must be accounted for, so the sum of all the oxidation numbers must equal the charge of the species. Rule 5 says that, although there are compounds in which the atoms of a particular element have different oxidation numbers, it is easier to treat them as if all the atoms of an element have the same oxidation number. Let's try to balance this equation using oxidation numbers. First, let's identify the elements that are changing oxidation numbers. Here's a hint. Most of the time, If oxygen and hydrogen only appear in compounds in the reactants and products, then their oxidation numbers do not change. So let's focus on the other elements. Copper is 0 in the reactants because it is a neutral element, and it is +2 in the products. It's an ion with a charge of 2+. Nitrogen is +5 in the reactants, 3 times -2 for oxygen, plus nitrogen equals -1, and +2 in the products. Nitrogen plus -2 for oxygen equals 0. So copper is oxidized and nitrogen is reduced. Next, we balance the total change in oxidation number. The oxidation number of one element will increase and the other will decrease. The total changes must be balanced since the number of electrons will be the same. Each copper atom changes from 0 to +2 for a change of +2. Each nitrogen atom that changes from +5 to +2 for a change of -3. To balance these changes, we need to multiply the copper by 3 and the nitrogen by 2. Note that we only place the coefficient on the part of the nitrogen that has been reduced, since we have nitrogen that is not reduced as well. Once the oxidation-reduction is balanced, we can finish the balancing in the traditional way. There are 8 nitrogen atoms in the products, so the coefficient of HNO3 must be 8. This means there are 8 hydrogen atoms in the reactants, so there must be 4 H2O in the products. Checking the oxygen, we find 8 times 3 equals 24 in the reactants, 3 times 2 times 3 equals 18, plus 2 plus 4 equals 24 in the products. So the reaction is balanced.